All right, so this segment is about carboxylic acids and how to react those, because it turns out carboxylic acids actually have different reactivity sites. You can see there's a hydrogen here that the other derivatives do not have. If you look at these derivatives, there are no hydrogens explicitly drawn in here that are acidic, okay? So we're only talking about chloride, oxygen, nitrogen, not an O with an H on it. So in this kind of situation, a nucleophile might compete with various electrophilic sites, either acidic protons like this one, or even this one, or even the electrophilic carbon itself right here, delta positive. These are all delta positive. So how do we know where it's going to attack? So from studying a bunch of reactions, we can tell under certain conditions when it attacks one over the other. For now, let's go ahead and practice our finishing these reactions. Let's do the first one together. So if it attacked the carboxylic acid hydrogen, if we had a nucleophile that was basic and attacked here, then we would have a carboxylate, and then we would have the rest of it. Okay, so there's that, and the nucleophile got protonated. Okay, so go through the rest of these and go ahead and draw me the products, and then we'll talk about it. All right, guys, so I've got my carboxylate here, and then I have my alpha hydrogen was deprotonated, making it negatively charged here with 2 hydrogens. And notice there's some resonance here as well. My pen's not working right now, but there's some resonance there. Let's see, right here. All right. And I also have this tetrahedral intermediate. So if we look at the stability of these, I think you can see that this one does not have resonance stabilization, so it's the strongest. So probably it's going to be more like this reactant favored. Whereas here, this is resonance stabled with the carbon, and this is resonance stabled, so the negative is on both oxygens. So I think for that reason, you can see that often we prefer to do this. Therefore, nucleophilic attack of the carbonyl carbon is not as likely. So that means that they do not we do not take nucleophiles and attack the carbonyl very often unless we have other conditions which make the electrophilic carbon more electrophilic. And we did learn that in acidic conditions, we can protonate this and activate it, making a weak nucleophile more likely to attack here. Okay, so these are reactions where we can start to do things with carboxylic acids, usually acidic conditions. All right, if you had a strong base though, the reason why this wouldn't work is because strong bases prefer this hydrogen right out here. All right. Okay, so I think you can answer these questions, and let's work through electron step-by-step mechanism. Well, we already did the first step, which was activation of the carboxylic acid or carbonyl group. So we have an R group, and we have now the nucleophile attacked, making this an OH single bond. Okay, I think you guys know what to do from here. We do probably some proton transfers. We want to incorporate this ester group, so that's something we want to keep. So we want to try to get rid of maybe some of these. We want to get rid of this OH group right here. All right, so my goal is to try to get rid of this OH. I probably want to protonate it from solution. So I'm going to show this getting protonated. Just very similar to how we've been practicing already in chapter 19 stuff. And then also another alcohol can be used to deprotonate down here. And I deprotonate that one because I want to keep that one down there. So I want to neutralize it and have it around. So this becomes protonated. This one gets deprotonated. This is likely to stick around longer. And at this stage, I can kick this water out And I want to end up with an OR single bonded, so I want to double bond with the O, so I probably want to bring these down like that and then kick out the water. I'm sorry, my pen is acting up. I don't think it's charged enough. Okay, so that is how we get this ester. All right, and we lost water, so that is one of the products which can help us with this equilibrium to shift the reaction forward if we can remove some of this water. All right, so notice very similar things to before. We talked about carbonyl activation with protons or acidic solution to make the nucleophile, which is weak, want to attack the carbonyl. After that attack, called addition, we do some proton transfers to set things up. We want this group to leave, we protonate it. We want this group to stay, we deprotonate it because it becomes neutral. And then we want to kick out the leaving group. All right, there's one more step I'm not showing, which is to deprotonate this carbonyl. So at some point you want to take alcohol, another alcohol, or whatever base you have in solution, which in this case is alcohol, and you can deprotonate that. I would maybe show that as a separate step though. Okay, hopefully you followed that. All right, transesterification is an example of this where you have actually some esters. So you're going backwards. You have esters, and instead of a carboxylic acid, you have one R group and you're replacing it with another R group. You can do the exact same kind of mechanism where the alcohol comes in and displaces this whole group. This is actually a triglyceride. These are esters linked by this 3-carbon backbone called glycerol. So you're going to have 3 esters. Triglyceride is a triester. We want to change it up. We want to switch out these R groups for this R group so that we end up with methyl esters. Okay, so I would love if you guys could try to figure out this mechanism, basically doing the same thing we did up here, okay, where this is your leaving group. All right, so go ahead and give that a try, and then we'll check our answers. All right, so go ahead and give that a try and check your answer in the key. Esterification can also be reversed by hydrolysis. Under the exact same conditions, you have acid, and now you've got water instead of alcohol. You want to replace the OR group with water, or an OH group, then you get carboxylic acid. Okay, so that's the same reaction, just different substances that you're switching in and out. The way to, so that probably tells you this reaction is very reversible then, right? We're basically doing this reaction one way, and now I'm showing you doing the reverse is the same thing. So how do you know which way you go then? If it's reversible, how do I favor one side or the other? And that's all Le Chatelier. So it's all in how much excess you put in of your starting materials, or how you remove a product. So there are different ways to do that. Excess water is very simple. We have plenty of water, so you can drive the reaction that way. So just think about those things. Now, we can't really use a strong base with acids, but we can use a strong base with esters. So instead of having proton activation, another thing you could do is to react this, you can use a strong base. A strong base doesn't need activation. It's ready to react right away. So if you have KOH, your nucleophile is hydroxide. So this will come in and attack and release the OR group as a leaving group. Now you might think OR minus is a strong base. It's not a good leaving group. But in strongly basic solutions, it is okay as a leaving group. So that's something new maybe for you. So carboxylate is your intermediate. Love for you to show me the reaction of how we can catalyze this reaction with base and compare that to how you catalyzed it with acid up here. Okay, can actually, you can use base or acid. They have different mechanisms though. All right, so check your answer there with the answer key. And then finally, you also have other carboxylic acid derivatives too. We talked about esters, acid chlorides. You also have amides. And amides can be hydrolyzed so that the N group is replaced with this OH group. All right. So you can think of a mechanism maybe where you have proton activation, or you have base come in and release this group. So see if you can figure out a way to do that. So there's one mechanism for each, doing an acid and then doing the base separately. Okay. A little bit more complicated mechanism here is with the cyano group. So here you would want to treat this CN group like a carbonyl instead of the nitrogen. Think of it like an oxygen, almost like a carbonyl group right here. So I'm sort of thinking this is similar to this. So that nitrogen can get activated, can activate this carbon here for attack. And to do that, the nitrogen starts off by getting protonated. And that makes this carbon more electropositive. And so then you'll have the nucleophile able to come in and attack. Okay, so that's if you have acid catalyzed. If you have base catalyzed, you don't do that. You don't have H+. So you just come in and just attack the carbonyl because you're strong base. You can do that. All right, so try to have two separate mechanisms. Just try an acid catalyzed one because they all follow the same kind of format. Activate the carbonyl, nucleophilic attack, proton transfer. And then with base, just attack the carbonyl, lose your leaving group, and then neutralize, okay? All right. And then lithium aluminum hydride, this is actually a more complicated mechanism because hydride is a strong base. You can't just use this as a shortcut. You would just grab this H and then you would be stuck. That would be the end. So there's actually a different mechanism for this. So I'd like you to consider drawing out lithium aluminum hydride. Lithium's just a counter ion. Don't worry about that. You don't even have to draw that. For this mechanism, you'll actually need to draw out the full thing, which is this. And you'll need to use this hydride to attack here first and then see what happens in the next step. It'll interact more with this whole thing than we have done before. Okay, so come back here a little bit later and we'll go through the answer for that. Okay guys, at this point some of you may have been able to go through those mechanisms I outlined and they made sense to you. Checked with the answer key, checked with the book, it's all in there. But I'd like to take a moment right now on this video to go through the answers and just talk through them if that helps, okay? So going back, again, all these mechanisms are basically the same. We have a carbonyl group, a nucleophile attacking it. With the carboxylic acid, we do this under acidic conditions. And we basically just want to substitute. You know, I want this OR group instead of this OH group. So I just do the necessary proton transfers and have the leaving group leave. So now that my pen's charged up again, I think I can walk through these with you guys. The basic idea for a mechanism here is I've got a catalyst. And we usually use an acid catalyst or an enzyme of some kind that helps. In this case, we have the catalyst that helps with having this attack here. All right, and we would have the elimination occur like that. And it would do that 3 times. So that is, we'll take another methanol, attack it here, and do the exact same thing here. Tack it there, and we eliminate, eliminate, eliminate. Yeah, this is a bit of a mess, and I don't recommend you do this. So, but basically is the idea of how we regenerate this glycerol here, how we generate it. Okay, is from that getting protonated eventually, and then we have this these ester groups here. Methanol with this part, acyl group, another methanol with this acyl group, another methanol with this acyl group will make 3 separate esters. They're no longer chained together by this glycerol. Okay. All right, carboxylic acid would not react, whoops, somebody doesn't know grammar, with an amine to make an amide under acidic conditions. Draw that out. Okay, so if I had a carboxylic acid with an amine, so I will have NHHR. Let's say I have a primary amine. So why would it not do this? even under acidic conditions, and swap out the OH group for an NH group. And I think you might see that nitrogen is a bit stronger base than oxygen is, so it might be competing with this instead of attacking the carbonyl. It prefers to take the hydrogen. So this will prefer to get protonated like that, and then you'll end up with your carboxylate, which is resonance stabilized. Okay, so probably not the best thing to do there. So there's a different way to make an amide, but the basic idea here is it does not attack there to make an amide. So it would be nice if it did. So either H or R, it's up to you. Okay, so yeah, something to think about then is how strong your bases are and how to really get them to attack the carbonyl. And if they're a little more basic than usual, you're probably going to get more of that deprotonation here rather than attack at the carbonyl carbon. So what we're saying though is that alcohols and water are okay with attacking here as long as you have acidic conditions. And we try to drive the reaction forward using Le Chatelier's principle. All right, before we move on, it's already too many reactions, right? So I strongly recommend pausing the video and writing out the reactions that we've learned so far, which is carboxylic acid and alcohol, acidic conditions gives us the ester and water. And one ester plus an alcohol gives us a different ester. This is called transesterification, because we're sort of going across different alcohol groups, different R groups, swapping one R group for another, starting with an ester, ending with an ester though, so that's why transesterification. So draw this reaction out, summarize it for yourself. You can pick a simpler example, it doesn't have to be glyceride, but this one is really helpful. This one actually, by the way, is how we make biodiesel, for example. Vegetable oil has these triglycerides, and then you can cleave the turn them into esters that can be used for fuel. All right, so all right, once you have that down, then let's continue and we'll add to your list of these substitution reactions. Okay, this one looks very familiar, right? We did one where we have an OH and an ROH, and now we have the OR and an H2O. So basically that's the reverse. So it's going to be the same mechanism as you had up here for this carboxylic acid turning into an ester. It's called esterification. This one is the reverse, so this one's called hydrolysis. Hydrolysis usually refers to water as a reactant. Let's do this together. All right, first step was we need to make this more enticing. As an electrophile, we want the water to attack here. So we need to activate this. We need to make this positive, so it inductively pulls charge away from this carbon, making it more electropositive than usual. Then this can attack, and then we get this. Okay, and I'll show my water in a different color. There we go. There's my water nucleophile. And now the point of this is to have this OH group stay, because I'm trying to explain how I make a carboxylic acid. So I need this OR group to leave. So I'm going to have, now again, some students like to do this. I don't do that just because it's not necessarily what's happening. So, but if you do that, it's all right, I guess. All right. Okay, so I like to do that, but I'll just leave it up to you. It's now that's positive, and I have my OH group that's neutralized and ready to stay. At this point, it doesn't matter which hydroxyl group you use. You just want to use one of them, though, to kick out this leaving group like that. And that way you might ask, why am I doing that? Again, it's so that you don't have a carbocation there. Okay, and then I have been lately forgetting this step, but of course you have this protonated carbonyl group that you want to show deprotonate. So I use whatever I have in solution as my base, lots of water around, and that's how I get that. Okay, now this alcohol that came off is right here. The water that came in is right there. So everything's accounted for. And I regenerated an H+. This will turn into hydronium ion. So that's how my catalyst works. I used it to protonate, and I used it, and then I got it back. Okay, all these steps are reversible, by the way, right? Because the acidity or the basicity of water and alcohol is about the same. So we try to use tricks like Le Chatelier, try to have excess water push the reaction forward, or devise a way to remove alcohol at the end, perhaps distillation or something like that. Before we move on, write that reaction down, okay? Write this reaction down and know how to do the mechanism. Draw it out separately on a sheet of paper. Collect all your mechanisms. Okay, it's going to pay off. All right, base-catalyzed means we don't have that H+ here. We don't have that activation step, but that's because we don't need it. We have a nucleophile that's strong enough, so it just comes in and attacks. Once we have that, can you figure out what we do next? We don't exactly need to do any proton transfers because we're in basic solution. It's okay for things to be negatively charged. So what we tend to do at this stage is just drop these electrons down to begin with and kick one of these out. Now I just got OH on here, so I think I will strive for something different. And remember, hydroxide is a poor leaving group, alkoxide is a poor leaving group, but we're in basic solution. So in that kind of environment, it is not unusual to have these ions floating around. So you're going to have some alkoxide ion, like a methoxide, ethoxide, things like that, some kind of R group. Okay, so now that's not what they have here. So do you know why we draw it in this form? Well, think of the environment. We are in a basic environment, so the likely form of this is its conjugate base. So that is good to know. So unless you have a workup step, you're likely going to be the negatively charged group, which means you're water soluble, usually. Okay, at this point then you would have an acid workup step as step 2, and you could use water workup, or you could do, when they put H2O, usually they mean a little bit of acid. You just do dilute. H+ means water, acid workup in water. And then that protonates it. So you do need to have that workup step. All right, but otherwise pretty simple mechanism. So write that down, and then we'll do some more, slightly more complicated ones here. So basically the same though. So instead of OR group, we have an NR group, so an amine leaving group. Okay, and we want to substitute it with an OH group. So since this is not going to be a very good leaving group, we're going to need to protonate it eventually. But before we do that, we need to have an OH nucleophile. So there's two ways to do this. One is an acid catalyzed mechanism where we use H+, catalytic amount of H+ in water as our nucleophile. And then we can also have our base mechanism, which is going to have OH- with no need for H+, obviously. It would neutralize that. But then if you do base, though, you need to do a workup step in water or dilute acid. Okay? So let's see if we can do that. Acid workup means we would protonate. This would be our first step, is right there. Okay? Simple. And then, you guys know. And then, what's next? I think you guys know it's proton transfers. Okay, so I'm just going to show that is positive and that lost. Okay, so I'm implying proton transfers here. And then I have this, and then I have deprotonation of this hydrogen. And that's how I get my carboxylic acid at the end. Okay, all right. Did not do a good job on a color scheme, but anyway, that's my acid catalyzed. My base catalyzed, I've started in green here. I have R groups on my nitrogen, but they could be hydrogen. And you might think, well, OH would grab the hydrogen off of there then, wouldn't it? And actually, a negative charge on a nitrogen would be more basic than this OH minus group. So most of the time you're going to see that it attacks the carbonyl. So you can have a hydrogen out here if you want. All right, so in any case, we've got hydroxide attacking the carbonyl, and then you have this tetrahedral intermediate. Now at this point, what's likely to happen is the reverse, because hydroxide is a better leaving group than this amide ion. So when this collapses, OH would get kicked out first and we go backwards. So the way to drive this reaction forward is then to explain that would be to protonate this and make that a better leaving group first. So under basic conditions, water is acidic enough for this. And once we do that, now we've got a good leaving group with the nitrogen to kick it out. So because it will be positively charged at that stage. And after that, we're going to have our carboxylic acid. And our byproduct here is an amine. It's the amine generated from the amide, from this NH or NR2 group. And then over here, our leaving group was the same. Okay, for this one, the hint was that think of the C double bond N or C triple bond N, sort of like a carbonyl. And so I'm thinking it gets activated. And when that gets activated, it draws electron density this way, so that makes this carbon really susceptible for attack. So if you're in an acid catalyzed situation, then you will have water as your nucleophile. And I'll do that in a different color. Okay, at this stage, we're going to have a lot of steps. Okay, so see if you can follow this. That gets neutralized now. And I've got H2O that's attached. Now, look at what we're trying to make. So I need to have this either become this OH or the carbonyl O. Then I need another oxygen, and I need to get rid of this nitrogen. All right, so that's a lot. So first, I know I want to keep this group, so I need to proton transfer to get that more stable. And I know I need to get rid of this nitrogen, so maybe I will pick up an H there. And I already picked up another H right here anyway. Okay. All right, so now this is positive, and this is neutralized. And now I think you can see same kind of pattern, but we're tethered here. We're still bound there because it was a triple bond. Now it's a double bond. So eventually, though, we're working our way. It's like that song, "Working My Way Back to You, Babe." Remember that? It's an oldie song. Okay. All right. And then, see, now we've got a lone pair. We can protonate here again and deprotonate here. So let's try that. So proton transfer. So see, we want to eventually turn this into a good leaving group, which now it looks like a pretty good one. This one is here to stay. And then now you can see this is ready for attack. So it took all these steps just to get this into an amide. This is an amide, basically. All right. Now, when we have an amide, we can just go with this mechanism because we already did that part. So from an amide, you have protonation, and then you try to get rid of this nitrogen group. Okay? So hopefully you see that. This will, through the steps we just did above in the previous problem, will eventually get us to a carboxylic acid. Okay, carboxylic acid. All right, and then with a base, because this is also base-catalyzed as possible, then instead of activation, we have something strong enough to just attack the carbon right away. Then you can neutralize it with water, so protons from water, and then try to get your amide, and then follow the base-catalyzed route, including workup for that step. Okay, and here we are, last but not least. This mechanism is a bit challenging. I most likely won't ask you to do this. Perhaps for extra credit I might, but it is just it's just a lot of steps. So okay, but if you'd like to see it, I'm going to go through it now, but you don't have to memorize it. Okay. All right, so if you want to skip this part, that's fine. I won't be offended if you close your YouTube window. Okay, normally, like I said, when I see hydride like LAH or NABH4, I'm usually thinking, oh, that's just H minus hydride nucleophile. Okay, it attacks the carbonyl. But remember, we have this to deal with, this acidic hydrogen. So the first equivalent is actually going to grab this, but with this mechanism, it's a bit more complicated. Look at what's going on here. This whole carbonyl group is being reduced. So in this kind of situation, we need to figure out how we got the two H's on here. So there is a way to do that with this reagent. So let me show you how I do it. All right. First, I tell myself, oh, with a carboxylic acid, I have to use this molecule. I can't take a shortcut and call it H minus. All right, so what I'm going to do is I'm going to show you the full mechanism. And that is the first step is this hydride attacks here, and I get this carboxylate. All right, now you probably know that H2, all right, it's flammable, like the Hindenburg. Remember that Zeppelin that blew up in the sky? So this H2 then leaves this Lewis acid behind, AlH3. And now what's going to happen is this is electron deficient because it doesn't have an octet. This is looking for electrons, so it can attack there. So I can have this attack here. Or I could have this come in and this can attack there, either way. Okay, so let's say we do that. Now every time aluminum has 4 bonds, it's negatively charged because it's only used to having 3. All right, so now notice that I'm in a situation where now I no longer have that hydrogen. So this hydrogen that was a problem before, a problem child, now it's gone. So now I can take this, and this is still reactive because I'm bonded to 4 things now, and aluminum's negative, so that puts negative charge on this hydrogen by induction. Okay, so then this can attack, it's sufficiently nucleophilic, and now I have a hydride attack like usual, but I have this whole thing. See, you're not used to that yet. So that's the thing with this one. It's a little bit weird. All right, once I have that, then I have this tetrahedral intermediate, and I still have the aluminum attached. So at this point, we have this collapse down and need to figure out who's a better leaving group. So hydride is very small, so not very polarizable, but this can leave. So I can have something like this. Okay, so that's how we end up with an aldehyde as one equivalent. Now at this stage, you can think of the rest of this with just hydride. So now you're used to bringing this down, reducing it by using hydride ion like this. So you can just use that as a shortcut from now on because we no longer have that problem with the carboxy proton, the carboxylic acid proton. Alrighty, so there we go. Okay, and so step 2 is acid workup, dilute acid in water. All right, so that's the whole thing. So we needed to use this whole thing in order. Really, the key step is right here. So explaining that. But after that, we can just use hydride again. And so we definitely need excess in order to make this work, because you have 2 hydrogens right here. All right. Whew. As a challenge, you guys can do the same thing with amides or amides. Okay, so let me draw sort of an example of that. Is you can have an amide, which is a nitrogen group. It could be R groups or H groups. You can also do the same thing, excess LAH followed by acid workup, and you will get the carbonyl reduced all the way down. All right, so same kind of reaction, but with nitrogen instead of oxygen. So as a challenge then, you can work through this whole thing again, but with nitrogen. All right, you're welcome. All right, we'll pick up with the rest of this in the next video.